Okay, today we're going to be talking about another kind of function it's not really either exponential or logarithmic, but it's got an exponential function inside of it, so it is kind of related to exponential function. In fact, it has a lot of characteristics the same, but there's a little variation here. It's called a logistics function. So to start us out here, we've seen that populations have a tendency to grow at least exponentially or nearly so if the resources are unlimited. But it's often the case that resources actually are limited. At first, the growth looks like exponential growth, slow starting but picking up speed, concave up, increasing. However, as resources become scarcer, an inflection point is reached and the growth becomes concave down, still increasing, but it eventually levels out to horizontal asymptote, which is a limit of the growth, limit of the population. So an example of this for a logistics function might be the spread of a rumor or maybe a communicable disease. So let's take a disease for example. At first, each infected person will spread the disease, let's say, to 2 more people that they come in contact with. Well, in turn, each of those people will spread the disease to 2 more people. And so it will basically double each time period. Well, that's exactly exponential growth. And so remember, in exponential growth, it turns out that the rate of growth is proportional to the number already infected. So the more infected you have, the more growth you're going to get, because it's going to double in a certain amount of time. But if the population that's susceptible to the disease is actually unlimited, this will actually be your exponential growth. But sometimes there's a constraint limiting the growth. For example, if there's a limited population that's susceptible to the disease, like the people are contained in a certain city or a certain place, maybe they're on a cruise or something. There's a certain population there that it cannot grow beyond that. Well, what's going to happen is sooner or later, the infected person, when they try to, well, they're not trying, but they would be in contact with 2 other people that might be giving them the disease. Maybe one of them has already had the disease, so they can't spread it to as many people. And this starts happening quite a bit. Then the rate of the growth of disease will start to slow down and eventually will level out, and eventually everybody who's going to get infected basically has been. So this type of growth is modeled very well by what's called a logistics function, and it's actually proportional to the difference in the amount of people who have the disease and the people and that limiting amount. Okay, and so here's the formula. This is what it looks like. It looks like P of t, I'll use P for population, but it could be anything. So Y, or P of t, is A over 1 plus C times e to the kt. Now there's our e again, our good old exponential base there, our natural base. And so we have e to the minus kt. Well, that's like an exponential decay part right there, but it has the c in front of it. So basically this is kind of like has some similarities to some exponential stuff. It's kind of exponential buried inside it, but it's not really the same as exponential. So we're going to let a be some amount, and we're going to have, well, if a is positive, then we have a logistics growth function. And c and k are going to be positive amounts, but there's also a minus built in there. So the e will be to a negative power. So let's look at an example here. Let's say we've got a culture of bacteria, and it's modeled by the following formula. P of t is 1000 over 1 plus 2 e to the negative 0.2t. Let's look at what the graph of that looks like. You can pull that up on your calculator if you want. Here's a graph from Graphmatica. Now notice what happens here is, if you just look at this part over here to the left, it looks a lot like the beginning part of an exponential growth function. Horizontal asymptote of y equals 0 on the left, increasing concave up, very slow growth at the beginning, but then picking up speed and growing faster and faster. But look what happens. Now it's no longer like an exponential growth. Somewhere in here it reaches an inflection point. Sometimes that inflection point is called the point of diminishing returns. And now that's where it's actually growing the fastest, is at that inflection point. And then it starts to slow down in growth and starts to be concave down. And now it's still growing, but it's actually pretty fast still for a while. But then it starts to slow down growth, and look what's happening. It levels off and finally approaches a horizontal asymptote. That asymptote, if you look, is at 1,000, and that happens to be the same as this up here. So notice, look what happens here. As t gets bigger and bigger and bigger, this is e to a negative power, negative really big power. So the e to this power is getting close to 0. Let's just look at it in general up here. As t gets closer and closer to infinity, or really, really big, way out to the right, this e to this power gets close to 0. So c times that is close to 0, so that the whole denominator is getting close to 1, and the whole thing is getting close to a. So it's approaching this asymptote of y equals a. So a is the value of that y asymptote. So in this case, there's only 1,000 bacteria probably in the culture. Eventually they're all going to get or there's only the environment can only sustain 1,000 bacteria. Let's put it that way. So there's probably maybe in a petri dish or something, and it's got a limited environment, limited amount of resources, food perhaps, and so eventually it cannot grow beyond a certain level, and the population stabilizes. So what happens if we change the parameter a? And so here I've graphed in Graphmatica this same function here, or a function here, but different values of a. I'm graphing a over 1 plus 2 e to the negative 0.2t. So I've left the c and the k alone, but I'm changing values of a. And here I've done 100, 200, 300, and so forth up to 1,000. And you can see the graph here. Notice it still has the asymptote of the y equals 0, the x-axis on the left, but notice that the asymptote is changing. So we're basically getting a vertical stretch here. Which, of course, we know that's exactly what's happening. We get this is basically like taking 1 over this and then putting p, replacing y by y over a. So that's going to be a vertical stretch, changing the asymptote on the right. So it's changing the limiting value. Now I'm going to leave the limiting value to 1,000, leave this coefficient for c at 2, but I'm going to put in different values for k, 0.01, 0.02, all the way up to 0.1, just going up in increments of 0.01. And take a look at this. If you'll notice, these don't change the y-intercept, so the y-intercept is the same. That ends up not changing the, if you think of y-intercept as your initial amount, it's not changing that. If you go on into the negatives, notice that they still have the asymptote of the x-axis. In fact, they'll always have that. But it didn't change the top asymptote. The limiting value was still 1,000, so the top asymptote is 1,000 there. But it does change sort of how fast it gets there. When the bigger the value, it's slower at first, but then once it gets to this part where it's growing fast, it goes really fast right through here. And so it changes from really low to really high very quickly. Whereas if you've got a smaller value there, so the 0.1 is this one that's more gradual growth all the way through there. Now what happens if we change the value of c? So leave everything else alone and change the value of c. And if you look, I think you can kind of see just by looking at this that this is just a horizontal shift. Okay? But not by the amount of c. See, I've got c's going up by 0.5, but the shifts are not all the same amount. Well, it turns out it's a shift by log of c over k. And we can prove this because we know what makes a horizontal shift. So if you have a over 1 plus c e to the kt, you can write c as e to the power log of c, natural log of c. Then we use property of exponents. This is e to the log c times e to the minus kt is e to the minus kt plus log of c. Factor out a minus k, and we get minus k times parentheses t minus log c over k. So now if you look at it from the, if you just done it with c as 1, and then now put in c, you see that we've replaced, essentially replaced t by t minus natural log of c over k. And so what happens is we are actually taking that original one, a over 1 plus e to the negative kt, and shifting it by replacing t by t minus natural log of c over k. So that's a horizontal shift by natural log of c over k. So anyway, the c is going to give you a horizontal shift. The a is going to change the limiting amount, the top asymptote, and the k is going to kind of change the shape of it a little bit so that how fast it starts to approach that. Okay, so here's an example, an exercise. Let's see if we can answer some questions about this. A rumor is introduced at time t equals 0. The number of people who have heard it by the tth day is modeled by the function n of t equals 500 over 1 plus 49 e to the negative 0.2t. So here are the questions I want you to answer. How many people initially heard the rumor? How many people will eventually hear the rumor? Fill out this table of values, and then when did the rumor first reach 200 people, over 200, and then attach a graph. Maybe work out a graph. You can do it in your calculator, or and then maybe also in Graphmatica. Okay, so there is exercise 1. Go ahead and do this and work this out. Come back when you're finished and we'll check it. Press pause now. Well, here are the solutions. How many people eventually hear the rumor? Well, how many initially heard the rumor? That's at time 0, so that's n of 0. We can do this without a calculator even. 0 in place of t. Negative 0.2 times 0 is 0. E to the 0 is 1. 1 times 49 is 49. Then you have this 1 over here plus the 49 is 50. 500 divided by 50 is 10. So 10 people initially heard the rumor. How many people will eventually hear the rumor? That's the value of that horizontal asymptote, which is the numerator there, 500. Okay, let's look at a table here. I put the formula in my calculator there, and then did a table. Again, you see 0, 10 there, and I put in the certain values that it asked for, and there they are. Notice we're at 499 people by day 50, so by day 50 we're almost practically there. When did it first go over 200 people? Okay, well, one way we could do this is by our calculator, is put in y equals 200, graph that along with the curve, and find that point of intersection there is 17.43, so it's sometime during the 18th day. And here's a Graphmatica graph. Asymptote of 500 there. If we continued over to the negatives, we would have an asymptote of 0. Okay, one of my colleagues asked me to do some work setting up some notes for a lab that he was doing, and he was modeling a way of determining how many species of, say, birds or something were in an area. And it's actually modeled pretty well by this kind of thing, logistic curve. Now this gives the idea of using regression for the logistics curve, and we do have a regression in our calculator for logistics functions. And so that we know two common ways things can grow, linear and exponential. Linear is constant rate of growth, exponential is constant percentage rate of growth. But if we have growth that's proportional to the if it's limited by some carrying capacity or limiting amount, then that is often modeled well with a logistics function. So a lot of things in biology, for example, are model well with Logistics Curve. And so I'll let you guys read the notes on this, but we've got a population that has a tendency to grow nearly exponentially if resources are unlimited, but if we limit the resource, then we get this logistics function that we've seen already. Okay, so here's our task. Our task is to try to determine the number of species of birds in a given region. So we can go out and make observations, and we count the number of species in the sample. And we repeat this process again. We'll likely find some new species, but we'll also observe some of the same ones we found in the previous sample. And each time we perform the process, we can record the number of new species found and the cumulative number of species found. If enough samples are taken, the cumulative number of species should level out to a horizontal asymptote at the value of the total number of species. And we can model this data with the logistics curve and use the number in the numerator of the formula as an estimate for the total number in the area. So for example, we may have gone out in 10 observations, and this is the number of new species that we find. Okay? Now, we're actually going to not only just look at this is not what we're doing. We're wanting to do the cumulative amount. So the cumulative amount would be 10, then 22, then 33, and so forth. So the total amount. This is reminding you that you need to turn your diagnostics on so that we can use the R-square values in our calculator to measure how good it will fit. Hopefully we've already got that set up from earlier in the course. And we're going to turn on our plot and set it up so it's a scatter plot. If you've already got plot 1 set up this way, you can turn it on and off by just going to y equals and then turning it on and off. Then you go to Stat Edit and type in the list. Okay, and so we put it in here. And actually, I'll let the calculator do a cumulative sum for me here. This is something we haven't done yet. So let's see. I want to put list 2 to be my actual data, my cumulative sum. So I use list 1 for my observation number, list 2 for the number of new species, list 3 for the number of new species. Type that in. And then what I did to get the cumulative sum is I just put the cursor on L2 right here, see that? And then type in cumulative sum of L3. Cumulative sum is under, let's see, list, which is second stat, right arrow to operations, and then it's number 6. And then this gives me my cumulative sum or running total. So 10 is the first one, 22 is the sum of the first 2, 33 is the sum of the first 3, and so forth. And so now my data is got a cumulative sum, and that's what I'm going to plot. So if I've already got my scatter plot set up, I just go to y equals and turn on the plot. I'm going to clear out everything else. And then I do zoom 9, zoom stat, to see what the graph looks like. Alright, well, what kind of graph would model this? Well, it's definitely not a straight line. We see some curving, look like maybe a little bit of concave up here, and then definitely quite a bit of concave down. There may be a power function or something might work, but a logistics model might fit it pretty well. So let's try a logistics model, and a logistics model makes sense in the context of the problem. So to do regression, then you hit stat, right arrow to looks like this, hit right arrow to go to calc, and you have different models to choose from. A linear model, number 4, we've used. There's 5 is a quadratic, a cubic, a quartic. Those are polynomial models. You will go down a little bit. Notice there's a logarithm, ln, a natural log, number 9. Okay. Number 0 is exponential regression. Number A is power regression, and B is logistics. C is a sine wave that you learn about in trigonometry, and then D is kind of a special one there, which you may or may not actually have on your calculator. But you should have a logistics one. So here it is. Go down there and hit enter. Okay. Now to get Y1, you can hit variables, Okay, go to right arrow to y variables, choose function, and number 1. If you've got the newer operating system, there's a shortcut to that. You can just hit, I think it's the alpha button, and then it's one of the things up here. It's F4. Like that to get your Y1 or whatever. Okay, and so you do logistics L1, comma L2, comma Y1. Notice the comma is right here, one button above the 7, and L1 and L2 are second 1 and second 2. So you can see that. And so you'll put this in, and this will give you a screen that looks like this. And notice it returns something of the form. Use C where it actually switches A and C from the way I put it. And instead of K, it uses B. But it's the same thing. So the C is what I'm calling A. That's the asymptote. The A is what I call C. And the B is what I call K. Okay, so you've got that there. And there is our model with everything put in place, which will show up actually if you hit y equals, show up as y1. So the most important thing we're interested in this point, at this particular one, is this top number. 62.4 is between 62 and 63, so you expect there to be about 62 or 63 species ultimately. And actually, if you do the cumulative sum, we actually found 63. So the model would predict 62.4 species of birds, 62 or maybe 63. We found 63. So it's likely that we've actually found the entire number of species present in the area. Okay, very likely. And we graph it with the curve. It's a pretty good fit. If you look here, this goes through the steps. We're doing the same thing with Graphmatica. And in Graphmatica, you can press this button up here to do the data plot. That's the button, this button out up here to put data in. Type in your data. You kind of have to manually adjust the window by going to Grid Range, View, Grid Range, manually fix the window like you would on the other calculator, but we don't have a zoom stat here. So get a good look. Then you can go over here to where it says Curve Fit, click on that, and you can choose some different models, one of which is logistics. There's also a polynomial model. So if you put a 1 there, that's linear, 2 is a quadratic, 3 is cubic, and so forth. It does have an exponential as well, and a power function. So it's got a few different models, not quite as many as your calculator, but several. And then, there you go, it'll graph it with the data points. Okay, and you can print it, you can copy it. If you want to get the whole screen, you can use print screen, and that copies it to a clipboard. Okay, so we've talked a little bit about logistics functions. We talked about what the formula looks like. We talked about what what happens to the graph if you change the different parameters. And we've seen a couple of real-world examples for it. And we've also seen how we can use regression to take some data that's approximately logistic and model it well with a logistics curve.